recording. All right, everybody, welcome to the review for exam 2, the second exam for this summer session. First thing we're going to do, and on YouTube, I'll try to put timestamps down below. We do it like the YouTube people do, and they point down. I'll put some timestamps down so you can jump to particular parts. First, I'm going to go over the solutions for homework 3, and then I'm going to go through an example that is a lot like homework 4, so that you'll have another example of that to work through. So let me pull up the solutions to homework 3 here and figure out how to screen share while losing all my chat. Super annoying. Screen share. Let's go with this middle screen and share. All right, so hopefully what you're seeing now is the solutions. And so if anyone has questions as I go, feel free to drop those in the chat. I'm trying to bring that back up wherever it goes. Throw that into the chat or just unmute your mic and start talking. So here is the homework 3. So there's a legislature with 3 members, each who has an ideal point and a policy space. It runs from 0 to 80. I mentioned in a couple of the different videos that increments of 8 are always nice because they're much easier to draw freehand. So if I were to draw this on the board, I would be drawing from 0 to 80, and then it's pretty easy to cut that in half by eyeball method and say 40, and then it's pretty easy to cut the 40 in half and say 20, the 20 in half to say 10, and then you can have increments of 5. So I'll often do 8, 80, or 800 for that reason. But anyway, so this is the space from 0 to 80. There are 3 voters, Nick Drake, Elliott Smith, Leonard Cohen, that have ideal points at 50, 45, and 60 respectively, and they have perfect information about their situation. That means they know the ideal points of the other people, and they can sort of backwards induce what their preferred 2 sets are. None of that is secret. And that becomes important when they go to propose something, right? Because they want something that will pass that is closest to their ideal point. So that perfect information is necessary for later on in the later part of the question. And the current status quo is at 40. So here we go. Got the status quo at 40. I've got my issue space from 0 to 80. I've got Elliott Smith here at 45, Nick Drake at 50, and Leonard Cohen at 60. So the next part it asks you to do is to draw everybody's preferred 2 set. So Elliott Smith definitely likes everything between 40 and 45. It's getting closer to his ideal point. It's very easy to see that. We're moving from 40 to 45. So those are all strictly preferred. And then, of course, because he has single peaked and symmetric utility, which we don't have to draw because we know all that matters is distance on the line then, that his indifference point between 40 is 50. So those are the bounds of his preferred 2 set, those 2 indifference points. And then everything inside of those 2 points is in the preferred 2 set, which is why we have these soft parentheses, soft brackets, is that 40 and 50 are not in the preferred 2 set, they are the boundaries of the preferred 2 set. Similarly with Nick Drake here, going from 40, the status quo, moving toward his ideal point, he definitely strictly prefers all of those things. They are in his preferred 2 set. And then looking at his indifference point from 40, which is 60, we know he also likes all of these. These are all also in Nick Drake's preferred 2 set. So his preferred 2 set is everything between 40 and 60, but not inclusive of 40 and 60. They are the boundaries. So again, that's where we have these parentheses. And then the last voter is Leonard Cohen. His ideal point is at 60. That's the point in the issue space that maximizes his utility. It would be at the peak of his utility function if we were drawing that. He definitely likes everything moving from 40 toward his ideal point of 60. We're going up on his utility function toward the peak as we move that way in the issue space. And because it is single peaked and symmetric, we know that he also likes a lot of these points. How far do we go until we're out of his preferred to set? Find his indifference point. His indifference point from 40 is 80. So he strictly prefers everything between 40 and 80 to 40. So that is his preferred to set. And again, 80, we just made it inside of the issue space. 80 is one of the points. 80 is his indifference point, so it still gets the soft parentheses, the soft bracket there, indicating that 80 is not in the preferred to set. It is the boundary of the preferred to set. So 79.9 repeating is in the preferred to set, but 80 is not in the preferred to set. So those are the preferred to sets. Any questions on drawing preferred to sets? Okay, so the next part of the question says, what is the majority rule when set? All right, well, we have 3 people. So what is a simple majority? Take 3, divide it by 2, you get 1.5, round up to the next integer, which is 2. All right, so we need a minimum of 2 overlapping preferred to sets. That's what defines the majority rule when set. So if I start here at 40, this one's a little easier because I don't have to check both sides, right? Everybody is to the right of the status quo here. So I start here, and at 40.000000001, right? We could go out a million zeros and then a 1. That is in the preferred to set of everybody. So that is in the when set. And as I move across here, all of these points, all the way up to 49.99, are in everyone's preferred to set. Then when I cross over and hit 50, I'm going to lose Elliott Smith. 50 is not in his preferred to set. In fact, it's his indifference point. So we don't know what he might do in that situation. So that is not in his preferred to set. But I still have 2 people. So I'm fine in terms of the when set. All the way up to 59.9 repeating, all right? That is strictly strictly preferred by 2 people, all right? So the when set is going to be everything between 40 and 60, but not including 60, right? And as often is the case, it turns out to be, in a single dimensional model at least, it turns out to correspond with one of the voters' preferred to sets. It's not always true. If we had like 99 voters, sometimes you get when sets that don't exactly line up that way. But for most of the cases we're going to see, the when set is going to be equivalent to one of the voters' preferred to sets. So the majority rule when set, and that's what this notation is right here, the majority rule when set of 40 is everything between 40 and 60, but not including 40 and 60, because at 40, they're all indifferent because the alternative we're considering is 40. And at 60, Nick Drake is indifferent and we don't know what he will do. So it's everything between 40 and 60, but not including 40 and 60. The next question, part D, says, tell me what the unanimity rule when set is. And we already talked about that, right? We talked about how there are 3 overlapping preferred to sets for everything between 40 and 50, but not including 50, because 50 makes Elliott Smith indifferent. We don't know what he would vote for. So the when set for the unanimity rule is where all 3 of them would vote yes over 40. So it's everything between 40 and 50, not including 40 and 50. And that happens to correspond to Smith's preferred to set, all right? So those are the majority rule and the unanimity rule when sets in a single dimensional model. And notice that in this case, one, there is a unanimity rule when set. In some of the examples we've done before, we didn't have a unanimity rule when set. And you can kind of see that right away. If everyone is on the same side of the status quo, like we have here, the status quo is at 40, and all 3 of the voters are on one side, in this case, the right-hand side, then there will be a unanimity rule win set. But if one of these voters was on the other side, we wouldn't have a unanimity rule win set, all right? But when you do have a unanimity rule win set, it is usually a subset of the majority rule win set, right? The majority rule win set only took 2 people to agree, 2 overlapping preferred 2 sets, whereas the unanimity rule win set required 3 people to agree or 3 preferred 2 sets to overlap everyone's. So usually you'll see this, if there is a unanimity rule win set, it is a strict subset of the majority rule win set. All right. Now we're going to do some of this proposing. All right. We're going to first do a single shot voting game. Leonard is the proposer. He is going to get to propose something. It's going to face the status quo. They're going to have 1 vote, and then whatever wins, if it's the status quo or the proposal, that's what becomes the new law or the new policy for this group of voters. All right. So what will Leonard propose? Well, Leonard, you might think, well, he wants to propose 60. That's his ideal point. That is what maximizes his utility function. That's actually not correct, though, because what would happen if he proposes 60? 60 would probably fail. All right. It's in the majority. It's the boundary of the majority rule win set, but it's not strictly in the majority rule win set. And the problem is that Nick Drake is indifferent between 40 and 60. So if Leonard proposes 60, he'd be rolling the dice. He might end up with 40. And he doesn't want to do that because he can get much closer to his ideal point. He just can't get his ideal point. So he could maybe, you might think it's a coin flip for Nick Drake, so he could get a 50-50 chance of getting his ideal point of 40, or he could for sure get 59.9 repeating, right? If he proposes that, it's in the majority rule win set, he would get that. It would pass because by definition, it is in the majority rule win set. So we don't even have to do an expected utility calculation to realize that that is a way better deal. A chance of getting a status quo that is 0.0000000001 away from your ideal is much better than a 50% chance of getting something that is 20 units on the issue dimension away from your ideal point. No matter what his utility function looks like, because it's single peaked and symmetric, it's always better to be right here than it is to be here, all right? No matter what the probabilities are, in fact. I guess we could come up with an insane probability that would make it worthwhile to take the gamble, but for all intents and purposes, we're not gonna say what Nick Drake would do if he was indifferent, so he's gonna take the sure thing over a probability roll. Last part of question 1 says now there's going to be thousands of rounds of voting, and each member will be allowed to propose multiple times. Will this situation have a Condorcet winner? And if so, what is it? So everybody's going to get to propose. They're going to go 1,000 rounds. All right. So we could draw this out like the extended majority rule example that I did in the slides, right? And I had Florian, Brittany, Aaron, and I forget who, Anna maybe, and we could go round and round and round and round, but we don't have to do that because we know by the median voter theorem, we will have a Condorcet winner because we have voters who have preferences that are complete, they have preferences that are transitive, they have preferences that are single peaked, they have preferences that are symmetric, so their preferences meet all the conditions, and it is a single issue dimension model. Therefore, the median voter theorem tells us that the ideal point of the median voter cannot be defeated in pairwise majority rule. It is a Condorcet winner. So all you have to do is say yes. If using majority rule, then yes, by the median voter theorem, we know there will be a Condorcet winner. And on an exam, I'd probably list out why the median voter theorem holds. I would say they have complete transitive preferences, they're single peaked, they're symmetric. We don't necessarily need symmetry for the median voter theorem, as it turns out, but we're going to have it, so go ahead and throw it in there. And it's a single dimensional model, so the median voter theorem's conditions are met. We will have a Condorcet winner, and it is going to be the ideal point of the median voter the median voter is Nick Drake. How do you find the median voter? Just start on each side and throw one person out on each side till you're left with only one person. That's going to be Nick Drake. So 50 is the Condorcet winner of this multi-round voting game. And notice the Condorcet winner is an alternative. A lot of people make this mistake on the exam. They say that Nick Drake is the Condorcet winner. Well, no. I mean, he wins in a way because he gets his ideal point, but a Condorcet winner is an alternative. It's not a person, all right? The Condorcet winner is an alternative that cannot be beaten in pairwise majority rule. It's not the person whose ideal point happens to be there, all right? It is the alternative that cannot be beaten in pairwise majority rule, all right? Then the last part, I just add this as a note for you. If using unanimity rule, of course, there's no such thing as a Condorcet winner. Condorcet winner is defined by majority rule. That is what it is for. A Condorcet winner, again, is an alternative that cannot be defeated in pairwise majority rule. But what if we wanted to think about a similar concept? Like, are there any alternatives that can't be beaten in unanimity rule? There are many of those. There are many alternatives that if we got there, they would have an empty unanimity rule win set. Specifically, all the alternatives that are in the single dimensional Pareto set. And you find that in a similar way that you find the Pareto set in 2 dimensions. You start at one person's ideal point and you go to the last person's ideal point, right? It's a one-dimensional model. We can't move around. Like I tell you guys to think about looping a string around one of the ideal points and then looping each ideal point in a 2-dimensional model. We don't have that because there's no other dimension here. So you start at one person's ideal point, loop the string, go to the next person's, loop the string, go to the third person's, loop the string. That determines the Pareto set. The Pareto set is everything between these two, and every point in that Pareto set would have an empty unanimity rule win set. I didn't ask you for any of that for part F, but I thought I would list it here because it is very analogous to what we do look at in a 2-dimensional model, all right? Okay, so any questions on number 1 before I move to number 2? Okay, so question 2 here, I gave you a 3-voter legislature, and they're attempting to reach some sort of bargain on some issues that has 2 policy dimensions. We see here dimension 1 and dimension 2. The legislature is using majority rule, and the indifference curves are all circular, meaning they have single-peaked and symmetric preferences, all right? Suppose member 2 and 3 reach some sort of an agreement on an alternative that is marked as the proposal. So let's say they're just talking amongst themselves, right? They're over here, maybe in past debates, they've been the 2 that have kind of had a meeting of the minds. So for whatever reason, they have come up with, hey, and we don't even know where the status quo is, right? And that's not actually important for answering any of the parts of the question, but they've decided, hey, what about this proposal? Let's maybe do that. Let's maybe propose that to face the status quo, all right? And so part A just asks you to draw their indifference curves to the proposal. So it's all points equidistant from their ideal point. So for member 2, it's this circle, all right? For member 3, it's this circle, all the points that are the same distance to their ideal point as the proposal. And for member 1's pretty far away from the proposal, so it's all of these points that are equidistant from the ideal point. And I just kind of chopped off these other quadrants of the Cartesian axis because nothing is going to end up happening in those parts of the Cartesian axis, and I wanted to zoom in on what's important. Some of you guys did draw them all the way out, that's fine. There was nothing here that said this was a closed issue space, that these alternatives were not in play. So it was fine for those of you that drew those all the way out. I just did that. I did draw them all the way out, but what I wanted to put in the solutions was zoomed in so you could really see what was going on here. If I draw this whole circle and this whole circle, then it gets kind of hard to see what's going on here in the place where something's happening. Part B says, demonstrate that there are other bargains besides the proposal that member 2 and 3 could make that would leave them both better off. So in other words, is there anything in both of their preferred two sets when we're considering the proposal? All right, so this is member 2's preferred two set for the proposal. This is member 3's preferred two set for the proposal. Actually, it's their indifference curve, and everything inside the indifference curve is the preferred two set. Let me be precise there. And we see there's lots of overlap here. There are lots of things they both prefer to the proposal. And moving along member 3's indifference curve, all of these, member 3 is indifferent to, sorry, whoa, I don't need that. I don't know where that came from. Member 3 is indifferent to these, but notice member 2 strictly prefers them. And moving along this indifference curve, member 2 is indifferent to those in the proposal, but member 3 strictly prefers those things. So everything on or in the lens makes at least one of them better off, and everything strictly inside this lens makes them both better off. So there's plenty of bargains that would make them both better off. All right, and that's what I asked for here, both better off. Okay. Then I wanted you to draw the Pareto set. The Pareto set is the set of all alternatives where if you move away from one of those alternatives, you will make at least someone worse off. All right, even if you make someone better off, you will make at least one person worse off. All right, so how do you find the Pareto set? What I told you in the screencast is it corresponds to a geometric idea called the convex hull. All right, and you don't even have to remember that it's the convex hull, but what you have to remember is how to find it. And so the way to find it in 2 dimensions is, imagine this is a pegboard and we're looking at it top down, and member 2's ideal point is like a peg. I don't know if your mom's had one of these things. I always think of like my mom had this tray to hold casserole dishes when you were like taking them to like your grandma's house for a holiday. And it had wooden pegs you would put in so you could make sure that the dish didn't slide around, and it would give you handles to hold it. That's what I'm always imagining. But imagine like a pegboard with a grid, and there are wooden pegs stuck into it. And then tie a string around this one, and then as you move, make a loop around each member's ideal point that are on the edge. That's the Pareto set. And usually it's a tidy little geometric shape. In the case of 3 people, it's going to be a triangle. All right, it's going to always be a triangle. If somebody was out here, then we would go out here and do the loop, and we would get kind of a different shape if we had 4 voters. If somebody is in the middle here, though, notice they're already inside. All right, they're already inside. So that is the Pareto set. Any questions on number 2? Okay, so now number 3. Oh, is that somebody? Got a question?
Hello?
Okay. Now, number 3, same 3 voters, but I asked you to do some different things, all right? So member 2 and member 3 have reached an agreement, reached a proposal that we're gonna consider here. And then I ask you to draw the preferred two sets. I say of the status quo. Sorry, that's a typo. Everybody on the homework got it correctly though. I should have labeled this the status quo in both places or the proposal in both places. So I will fix that and re-upload it. No one got it wrong because of that, and I think one person at least pointed out to me that they were assuming that the proposal equaled the status quo, and they were correct. Sorry about that. This is homework 3, 6. Also, Okay. So the preferred two sets, again, it's all the points that are equidistant from the member's ideal point. So for member 2, it's a circle that runs through the proposal centered on their ideal point. They have single peak symmetric preferences. So that utility mountain has its peak here. And this is a level curve of that utility function, like a topographical representation of all of the alternatives that are the same height on his utility function. Don't ever forget that that's actually what we're modeling here. We just don't need to draw that utility dimension 1. It gets tricky because it's 3 dimensions, but we don't need to draw it because we've assumed single peak and symmetric preferences. For member 1, his indifference curve runs through the proposal and is all of the alternatives equidistant from his ideal point. Same thing with member 3 here, all right? And then I ask you to tell me what is the win set. All right, what is the majority rule win set? So the win set for an alternative using a particular voting rule is the set of alternatives that will defeat the alternative using that voting rule. So we have a majority rule win set, and we've talked about a unanimity rule win set. And I see I have another typo in the solutions here. That should say the unanimity rule win set is the set of alternatives that will defeat the alternative in pairwise unanimity rule. So that's obviously a typo. 3B. So that's the definition. So the majority rule win set is the set of alternatives that will defeat the alternative in question using majority rule. The unanimity rule win set is the set of alternatives that will defeat the alternative in question under unanimity rule. And then I want you to show me the majority rule win set and the unanimity rule win set. So first let's go backwards. Let's start with the unanimity rule win set. So the unanimity rule win set is where all 3 preferred two sets overlap. So it's obviously none of these out here. That's only one person. It's none of these up here. It's definitely none of these out here. Nobody prefers these. It's none of these out here. That's only one person who prefers those to the proposal. These that are in purple but not also yellow are where 2 people prefer those alternatives over the proposal. And then this lens right here is where all 3 of their preferred two sets overlap. So that's the unanimity rule win set, all right? And then moving on to the majority rule win set, we see here that the stuff in purple, including this stuff in yellow, is the majority rule win set. At least 2 preferred two sets overlap. And in fact, in here, all 3 overlap. So all of that, these kind of weird shaped, they call them petals. Here they don't look so much like petals, but these areas are the majority rule win set. All right, any questions on that? Okay, oh, here we go, picking me up. All right, so we have a question, give me a second to read it. So someone is asking, do they have to do these in a digital drawing program? You absolutely do not. Especially for the exam, you do not need to hand draw them. I mean, you do not need to do them in a computer. You can do them if you'd like to. Otherwise, you can just freehand them and just get them as close as possible. I think there was only one person out of everyone who hand drew them. I think it was on this one. They did a little oval and it hit the proposal, but it kind of like went like that, right? Let's see if I can show more carefully what I'm talking about, since I am here in a program. They did something like, and of course it wasn't perfect because it was hand drawn. That wasn't the issue, but oh, I don't get a rotation. Oh well. They did something that was sort of like this, right? And that's, you know, that's a little too close to not being okay. If you have a compass at home, you know, like from drafting or whatever, or from a geometry class, that's fine. But as long as you freehand it roughly correctly, I'm fine either way. I mentioned in one of the screencasts that in Keynote, at least, it's really easy to draw these circles that are centered on an ideal point. But not everybody has Max. Not everybody's super comfortable in Keynote. I draw these all the time, so it's pretty fast for me, but you are not required to, in any way, shape, or form, do them digitally. What I'll have is I'll have a grid like this, and you can print it out and draw it by hand and snap a picture or whatever method you're using to get me that PDF back. So you absolutely do not need to do it digitally, all right? Okay, so last question. Assume there are 5 members of a voting body, A, B, C, and D. They have ideal points in a 2-dimensional space. And I'm now giving you precise Cartesian coordinates. 1, 4, 4, 4, 2, 2, 1, 1, and 2, 1. Where the first coordinate gives their ideal policy on the X dimension, and the second coordinate gives their ideal policy on the Y dimension, using traditional X is horizontal, Y is the vertical dimension. All votes are taken over XY policy bundles. That just means that the alternatives and status quos are, the way you tell me what it is you give me the coordinates of it, all right? In ordered pairs, X coordinate first, then Y. Is there an equilibrium, all right? Well, let's go down here. Here are our voters, A, B, right here, C, and D. So I've already got a bunch of other points, but those are our voters. Was it 4 voters or should be 1 more? A, B, C, D, and E. Where is E? Oh, there's D and there's E. A, B, C, D, and E, all right? So basically the first question, which says, is there an equilibrium? Well, it's asking, are the plot conditions met? Is there radial symmetry, all right? Let's see if I can get my drawing tool out here. Remember, for radial symmetry, first, one of the alternatives has to be kind of be in the center of the cloud of dots. So if C was over here, right, we would already fail that condition, all right? If C was over here, we would already fail that condition because they would all kind of be in a circle almost. But C is sort of in the middle of a cloud of dots. So now I need to check if I start at each ideal point and go through C, do I hit another alternative? If I do that for all possible ideal points, then radial symmetry is met, the plot conditions are met, and there is an equilibrium. But notice the very first one I check here, voter A, I go through the person in the middle of the cloud, and I don't hit another ideal point, all right? So I've already failed the conditions of the plot conditions, so they do not hold. And they rarely ever hold, right? It's a really unique distribution of ideal points where you have that perfect symmetry around a middle point. I don't think it holds for any of these ideal points. I don't think even one of them do you hit another. All right, you might argue that D is pretty close. So maybe between B and D, they meet it. But for A and E, going through C, I don't come anywhere close. And it has to hold for everybody, right? So we don't have radial symmetry, therefore there is no equilibrium. All right, that's part A. Part B says, okay, there's no equilibrium. Can you construct an agenda of votes, of pairwise votes, that would eventually get you anywhere in the space? All right. And the answer is yes. If the plot conditions don't hold, you can always construct a set of votes that will reach any point in the issue space. You can always do that, all right? And then part C said, if yes, then give me those points, all right? So I first set 1.4, 1.8 to face 2.2, and it wins. Then, so I call that point 1, proposal 1. Then I have proposal 2, 2.6, 1.8, face proposal 1, and it wins. And all the way down, it takes me 11 moves here, but I eventually get to 4, 4. And I had to go negative a little bit to even get there. And this just shows you each of those. So first I had 1 face C, and it won. Then I had 2, face 1, and it won. Then I had 3, face 2, and it won. And you can use that cut point method to find those alternatives. All right. And if you had one of these on the exam, it'd be much simpler. This one was a little tricky. I mean, it wasn't, I didn't mean for it anyways to be extremely difficult, although I realize some of you told me in the comments on the homework that it did take you a while. I didn't intend for it to be that way, but it is one where some of the cases are pretty easy. You can just have vertical or almost horizontal cut lines, and you can find a ton of alternatives that beat the status quo, and it's pretty easy. I would give you something more like that if I asked you to do this on an exam. It would be much more straightforward. What makes this one tricky is that C and E and A and D have the same coordinate for their horizontal axis. And that makes it tricky to find those cut lines to blow this thing out far enough. Notice I had to come all the way out here before I was able to pull it back over and get myself here at point B. So it was just kind of, and notice I'm swinging back and forth. I go from 0 to 1 to 2 to 3 to 4 to 5 to 6. Notice I'm swinging across this person who's kind of in the middle, right? They're the one causing me problems. When you draw, if you were drawing out all the preferred 2 sets, you would see it's them. They're the ones they're always the person who's a little tricky to get them where their preferred 2 set overlaps. And it's not surprising because remember, for these 2 voters, we had part of the plot conditions met, but for these 2, we didn't. So it's not surprising. It's that person who's kind of in the middle of the cloud who it's so tricky to find things they prefer, all right, along with some other coalition within the group, all right? And of course, that's an illustration of the McKelvey-Schofield chaos theorem. Should have won the Nobel Prize for it, but never happened, unfortunately. Okay, any questions about homework 3? And I will move on to an example of homework 4. And I will update those 2 typos. Just make sure my notes make sense so I'll remember at the end of all this to do that. Okay, so here is the homework. And this first question basically wants you to run all of the 5 different, what is it, 6 different? 6 different voting rules that we talked about in chapter 7. Right? And the slides for chapter 7 were basically one long example of this problem where I take you through each one. So I'm going to do another example. I'm only going to make there be 3 groups just in the interest of time, but that way you'll have seen another example of this question. All right. So let me move over here to, and now I lose my, oh no, I don't lose chat. Yay, it stays on top. Good. Let me go back to the beginning here. And first of all, let me explain this notation here. I say in the homework what it means, but it's the same as this, all right? It's the same as this representation, right? This first group prefers hot tamales to Skittles, to Lindt truffles, to Reese's cups, to Baby Ruth, sorry. We live near the fire station also, not just the, we live near the hospital, the post office, and the fire station. So it can be loud here sometimes if exciting things are happening. So this is the same. This group of 10 voters strictly prefers hearts to clubs, to diamonds, to stars, to spades. That's their strict preference ordering. And then their approval threshold is everything above this bar. Just like for this group, their approval threshold was everything in green. All right. So this is the same sort of representation as this. So what I'm going to do for this example, I'm just going to translate it into this because this is a little easier on the slides to follow. But this is the exact same thing, okay? Hearts to clubs to diamonds to stars to spades for 10 voters, diamonds to stars to clubs to hearts to spades for 9 voters, and spades to hearts to diamonds to clubs to stars for 12 voters. And the green represents their approval threshold, all right, which we only need for approval vote. So first, let's look at plurality rule. It's the simple one. Each voter is just going to vote for their top choice. So 10 voters are going to vote for hearts, 9 voters are going to vote for diamonds, and 12 voters are going to vote for spades. And you see I have the vote totals already over here. Nobody's voting for stars, and nobody is voting for clubs. So simple plurality rule, most votes wins, spades wins. All right, so that is simple plurality rule. Now what about for the tweak of that, the first tweak of that, plurality runoff? Well, you run the same thing in the first round. Everybody votes for their top choice. Vote totals are the same. 10 for hearts, 12 for spades, 9 for diamonds, right? These 10 for hearts, these 12 for spades, and these 9 for diamonds. But then what you do is you eliminate all but the top 2 vote getters. So I'm going to get rid of the 0, let me say it this way. I'm going to get rid of the 0 for stars, the 0 for clubs, and the 9 votes for diamonds, and look at what we have left. Now I'm going to rerun the vote. All right, I'm going to rerun the vote. And in fact, it looks like I didn't do that correctly. So let's fix it now. I was in a rush because our faculty meeting ran long. So I need to get rid of, for this second round, I need to get rid of everything but hearts and spades. So let's do that. Okay. So now we have everything but hearts and spades is gone. And let me just do it for the next slide there. And so now the vote is actually 10 for hearts plus 9 for hearts, right? Because this group here is also going to vote for hearts for a total of 19 to 12. So that is the totals there. And then I need to update this slide, which was wrong. And so the winner, the winning alternative, come on thing, what's going on? All right, it doesn't want to let me. The winning alternative is going to be hearts, right here, all right? So that is how you do plurality runoff. You drop all but the top 2, and then you run it again. All right, so now what about plurality sequential runoff? All right. So in this case, we're going to do a similar kind of thing, but we're not going to drop all but the top 2 after the first round. We're going to drop the lowest vote getter after the first round until we're left with 2. We're just going to do that sequentially. So here's the first round, same as always. 10 for hearts, 12 for spades, 0 for stars. Nobody lists stars as their top choice. No votes for clubs. Nobody lists clubs as their top choice. And 9 votes for diamonds. 9 people list that as their top choice. Now, instead of dropping all of these like I did before, I'm going to drop the lowest vote getter. If there's a tie, then flip a coin. All right, you flip a coin. In this case, it doesn't really matter, but I'm going to drop stars first. All right. So I'm dropping stars. I'm left with hearts. So this should be, I left a slide out. Let's see. So which one did I drop? I dropped stars. So stars gets dropped. So stars is going to be dropped. So let's get rid of stars here. All right, and then we're going to, actually let me do this just for the future. So stars is going to be the first one dropped. And then here you see I've dropped all the stars. And so now, what happened? Right here. All right, so now stars has been dropped. All right, so now I need to let everyone re-vote. So this group is still going to vote for hearts. This group is still going to vote for spades. And this group is still going to vote for diamonds. And clubs is still going to get no votes. All right, because there's no one who ranks clubs as their top choice. So I need to get rid of the lowest vote getter again. In this case, there's no tie. It's easy. We're going to get rid of clubs. What is going on here? Sorry, I didn't have time to run through this. Because our meeting went long. Oh, I see. I left stars in here. Okay, so now, all right, so now clubs is the lowest vote getter. I'm going to get rid of clubs. All right, and we will see that right here. Get rid of clubs. All right. I should delete these because we don't know what the vote's going to be yet. We haven't retaken that vote yet. Same thing here. No, right. I have to go back and redo it, but I will post these slides with these corrections so you guys will have them to work through. So now that we've gotten rid of clubs, right now all we've really done is gotten rid of the two that got no votes in each round. So now we're left with these three. So let's let them vote. And we get, sorry, we should have 4. What did I do? No, stars should have been gone a long time ago. So we're left with these 3. Get rid of stars now. So these 10 vote for hearts. These 9 still vote for diamonds. Need that star out of here. And these 12 still vote for spades. So notice no one's top choice has been dropped yet, so we're still getting the same vote totals, right? That's just so happens how this particular group, I kind of made this group up randomly, right? The one we did in the screencast was designed to give us different outcomes so that you could see that that's true. But sometimes that doesn't happen. Sometimes you get similar outcomes depending on the voting. So anyway, so now we're going to drop the lowest vote getter, and that is diamonds with 9. So let me now drop diamonds. We don't know what the vote will be yet. So we'll drop diamonds, 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 right? So we had diamonds. It was the lowest vote getter. Now we're dropping it, all the diamonds. We end up with just these 2. This is our final round of plurality runoff. And so we see that 10 will vote for hearts, 9 more will vote for hearts, and 12 will vote for spades. And so we're going to get 19 for hearts and 12 for spades. So hearts will win that one. And let's see, what did we get for the first 3? So hearts won plurality runoff, and spades won original plurality. So we have had some difference, all right? Now on to board account, all right? First, any questions on the plurality family? Okay, so board account, here are the voters. So now we're going to use a scoring rule, which is board account is a form of scoring rule, but it's the simplest scoring rule. It's one where they rank them 5, 4, 3, 2, 1 if there are 5. In the slides, in the screencast, I did 4, 3, 2, 1, 0. I'm purposefully doing it a different way here so you can see it doesn't really matter. As long as this is a strict ordering and they are only 1 unit apart, the answer is going to be the same. So 4, 3, 2, 1, 0 was Borda's original way of doing it. I like 5, 4, 3, 2, 1 because I'm not a computer scientist. I don't like starting to count at 0. I like to start counting at 1, right? So that is the way I'm going to do it. So now I'm going to come across here and look at, first I'm going to go group by group, all right? I'm going to say, what are the points that group 10 is giving to hearts, spades, stars, clubs, and diamonds? And here we go. This group of 10 is giving 5 to hearts, 4 to clubs, 3 to diamonds, 2 to stars, and they're giving 1 to spades. All right, so 5, 4, 3, 2, 1, 5, 4, 3, 2, 1. Now let's do our group of 9, and we're just going to add that number of points together here. Our group of 9, they're going to give 5 to diamonds. Notice diamonds is their top choice. Whoops. Go. Diamonds is their top choice. So diamonds gets the 5. Their next choice is stars. Stars gets 4. Their next is clubs. Clubs gets 3 points. Their next is hearts. Hearts gets 2 points. And their least favorite is spades, which get 1 point. So it's going to be 9 times that number of points for the group of 9's contribution. Moving on to the last group. And I got my little blockers here off just a little bit. This last group of 12, they like spades the most. They like hearts second most, so they give it a 4. They like diamonds third most, so they give that a 12. They like clubs next to last, that gets 2 points. And then stars gets 1 point here at the bottom. That's all of the groups. So now I can multiply those together and see that hearts gets the most points. So by board account, hearts is the winner. All right. And that's as far as I got because the faculty meeting ran long. So now you're going to have to bear with me as I go through the Condorcet procedure, which is the long one. All right. So here are our voters and their preferences, just the same as before. And here is the way I like to do the Condorcet procedure. I like to put the vote total of the alternative on the row in the cell. Of course, there's nothing here. There's no vote between hearts and hearts. So between hearts and spades, the number I put here will be the hearts total in that pairwise comparison. Condorcet procedure, remember, you run everything pairwise, right? One at a time, one pair at a time, I should say. All right, so first, there's not gonna be any totals here. And then first, and this is where I'm gonna have some numbers coming in that are wrong and I'm gonna have to fix them, but we're gonna run hearts against spades. So over here, hearts against spades. So, oh man, come on. Let me do it this way, since they're not finished. I'm gonna be editing a lot. Hearts against spades. Oh. Wish these cleared a little. Oh, they do clear easier, good. Okay, hearts against spades. Oh, come on, thing. All right, so what's the total for hearts? The total is going to be 10 plus 9, right? Both groups rank hearts over spades. So for hearts against spades, it's 19. And then for spades against hearts, right, the row is where I put their total, that's going to be 12. All right. So that is the total there. I'm going to need get rid of this and this and this, and now go to this one. All right. So this one is going to be, oh, it didn't work like I wanted. There we go. All right, so now hearts against stars. All right, so hearts against stars. All right, so hearts against stars. Hearts gets 10, none from them, and 12 over here. So that's 22 hearts against stars. And then down here, stars against hearts, it gets 9, right? Because the row is the total for that pair. All right. So get rid of that slide and that slide and this slide. All right. Now we are on hearts against clubs. Whoa, what in the world? Oh, I was looking for images to find these different symbols. So now we're doing clubs against hearts. All right, so only clubs and hearts are needed. All right, so clubs against hearts. So hearts gets 10, he gets 0 here, and he gets 12. So hearts are going to get 22 again. And clubs are going to get, clubs against hearts are going to get 9. All right. And we don't need this, 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 do need this. So now we're doing, one that always comes to the front, but we're doing hearts against diamonds. So there we go. So hearts against diamonds, hearts gets 10, doesn't get any here, but it gets 12 here. So hearts against diamond also gets 22. Oh, that didn't work, something went wrong. Yeah, that's right, that's right. Okay, this is something. Okay, so hearts against diamonds again, hearts gets 10, hearts gets 12, so hearts gets 22. And then diamonds against hearts, again, what is the row here? Number, that's gonna be diamonds total in this pairwise comparison, gets 9, all right? So far, those are the pairwise that we have done. And let me get rid of a few. And now we have this one. We have spades against hearts. Okay, so spades against hearts. I'm sorry, spades against stars. All right, so spades against stars. For spades, they're going to get 12. And for stars, they're going to get 19. Right? So stars get 19, spades gets 12. We are slowly filling in this whole matrix. So the next one here is going to be spades against clubs. So let's get rid of everything that's not that. So spades against clubs. So how many does spades get? Looks like spades is going to get 12. And how many is clubs going to get? Clubs is going to get 19. All right. So spades against clubs is 19. Let me copy that. Only got a few more combinations to do. Oh, what was that? Yep. Yep. Now we have spades against diamonds. So let's get rid of everything that is not a spade or a diamond. All right. Diamonds is going to get 19 here. These two rank diamonds higher than spades. And remember, the vote total goes on the row, not the column, in terms of the pairwise comparison. And then, so spades versus diamonds gets 12. And you don't have to do it this way with this matrix. To me, it's easier. Once you kind of have the method down, it's easier at the end to see if you have a Condorcet winner. But you can always just list out all the pairs, this versus this versus this. And then it's kind of up to you to go back through those and judge whether there's a Condorcet winner or not. I didn't like this method at first when I saw it in some stuff for Shepsley, but I ended up liking it a lot. It actually makes a lot of sense once you kind of get down the rhythm of it and how it works. So I'm going to get rid of, we don't need that, we don't need that, we don't need that. So now we're doing stars versus clubs. In the back. So let's get rid of everything that's not a star and a club. All right, so this is stars versus clubs. So in terms of stars, not going to vote for stars, is going to vote for stars, these 9. And then this last group is going to vote for clubs. So stars gets 9 votes. Clubs in the pairwise comparison of clubs versus stars, clubs is going to get 10 plus 12, it's going to get 22. All right, so there is stars versus clubs. And it might be the last one here, or next to last. Just in the back is stars versus diamonds. I think maybe there's one more after that. So all right, so stars versus diamonds. Oops. Let me save. There we go. Stars versus diamonds, stars gets not 10, not 9, and not 12. So diamonds is strictly preferred to stars by all the groups in that pairwise comparison. So stars gets no votes in that situation, and diamonds gets everyone's votes. So that's 22 plus 9, that's 21. Wait, that can't be right. 31. Yeah, 31. All the votes. Is that right? 10, 19, 22, 31. Yes, okay. I struggle with the arithmetic sometimes. All right, we have one more pair to do, and then we'll be able to see what's going on here. And that is clubs versus diamonds. Arrange, send it back. Okay, get rid of all these. Okay, now, clubs versus diamonds. This group is voting for clubs, 10. This group is voting for diamonds, 9. This group is voting for diamonds, 12. So clubs is going to get 10. And diamonds is going to get 9 plus 12 is going to get 21. And that is all, finally, of our pairwise comparisons. Oops. Yeah, I can get rid of that too. Let's just put it in there. Right here. Those are all our pairwise comparisons. So now we need to check, is there an alternative that beats all the others? So we need to find out how many we need. we have 31 voters divided by 2 is 15.5. Yes, I had to check that because I can mess up. So is there a row, right, where they get more than 15.5? And I think there is. Hearts gets more than 15.5 all the way across. And so I don't need all these things that I did in the screencast. In the screencast, I go through and I check each one. But in the interest of time, I've already kept you guys a while now. The Condorcet winner is hearts. He's the only one that has more than 15.5 all the way across, meaning it wins every pairwise. Not sure when these ended up being bold. It wins every pairwise comparison. Okay, so I'll just put that here for when you're studying. Hearts is the winner and is selected by the Condorcet rule or Condorcet method, I think we'll call it. Procedure is what Shipsley calls it. So Condorcet winner, but there's not always a Condorcet winner. Sometimes you'll go across here and there's not one that has more than half all the way across. All right. In that case, you say the Condorcet procedure doesn't, it gives us nothing. We don't know what it does. All right. It doesn't return a group choice. It's not decisive. Okay. Last one, a little easier, approval voting. All right. So approval voting is you vote for the things you approve of. All right. So hearts gets how many votes in approval voting? Well, it gets 10 plus 0 plus 12, right? So hearts is going to get 22. What about spades? Spades gets 0 from the first group. It gets 0 again from the second group. It's below the approval threshold. And it gets 12 from the top group. So total of 12. Stars gets 0 from the first group, right here. It gets 9 from the second group, and it gets 0 from the third group for a total of 9. Clubs is going to get 10 votes from the first group of voters. It's going to get 9 votes from the second group of voters, and it's going to get 12 from the third group of voters, so a total of 31. And then lastly, diamonds is going to get 10 from the first group, right here, 9 from the second group, right here, and also 12 from the last group right here, also 31. So approval voting returns a choice set of clubs and diamonds. So it is not unique in the choice set. Let's see, this is where I built it all in screencasts. Whoops, I deleted the last one, no, okay. So let me just put over here somewhere that approval voting returns 2 group choices Why is it doing this? So we're going to get clubs and diamonds. All right, so that's the end of that. All right, any questions about that? The different voting methods? And it does take some time to go through them all. Number 2 is on the homework. Consider an election between 3 candidates with the following vote shares: Davis, Owen, and Wren. Those are our neighbors in California. All the voters who voted for Wren strictly preferred Owen to Davis. Which outcome will win if simple plurality is ruled? So this is basically you using these vote shares just to run these. All right, so it's very similar to this, except instead of getting the numbers, you have to do it based on the vote shares. All right, and I think that's pretty straightforward. And then number 3, ask you to draw a spatial model. And each voter, it gives you their approval voting region. And then it asks you to think about this idea of independence of entry clones. The additions of an alternative identical to another should not cause the winner to change. So first, you have to figure out the plurality voting winner. And then you have to add a voter that is at the same spot as another voter and see if that changes the outcome. All right, so that is the method for doing that. So you set up this single dimensional spatial model, and then you say, okay, what would win under plurality? All right, then you add a clone first for the first person and see if it changes the plurality of it. Then you add it for the second person. Does it change the plurality? Then you add it for the third person. So what you're looking for is, does adding a clone of someone change the winner under these different voting rules? For some of them it will, or for some of them it won't. All right. One other little trick to tell you, for all of the pluralities, they're always voting for the thing closest to their ideal. All right. For Borda, they're going to rank them according to how far away they are from their ideal, right? So the closest thing to me gets the highest number of points. So that's how you'll assign the Borda. The Condorcet is pairwise. So once again, it's always whichever one is closer. And then for approval, I've given you their approval regions. They approve if something is plus or minus 2 from their ideal, and they don't approve for things further than plus or minus 2. Okay? And I'll be available to answer individual questions on either 2 or 3 via email or Zoom. I'm not going anywhere for the next 2 days. So please let me know. All right, any questions? Okay, so I will stop the video and I will get it uploaded as fast as it compiles. It does take these long, hour-long ones. It takes it almost an hour to compile and upload and then be processed by YouTube. But I will do that now. If I can even find where my controls are. All right. See everybody later. Let me know if you have questions.